Vesta is a brand new and highly complex navigation system designed by Boeing. It's what Starliner will use to autonomously dock with the International Space Station. VESTA stands for Vision-Based Electro-Optical Sensor Tracking Assembly, and here's how it works. The system consists of 2 laser-ranging sensors, 2 wide-field sensors, and 2 narrow-field sensors, all of which work together to guide Starliner slowly and safely to the station. Early in the rendezvous process, the sensors operate in a long-range tracking mode, monitoring the International Space Station from afar when it still resembles a bright, star-like spot in the distance. As Starliner gets closer, the sensors pick up more details and are able to see the ISS clearly enough to determine its outline. This phase is known as silhouette mode. Then, in the final phases of docking, the space station is close enough for the VESTA sensors to switch to feature track, where they use exterior features on the docking port of the Harmony module, such as handrails, stickers, and reflectors, to assess the capsule's position and attitude. Starliner's VESTA systems are programmed to recognize these features as relative points of navigation, enabling the spacecraft to determine exactly where it is and execute its docking procedures with great precision. VESTA also gives the ground teams a highly accurate understanding of Starliner's location relative to the space station, as Starliner autonomously makes its way to the orbital laboratory.
Alright guys, so let's do a quick pre-task for crew module to service module mate. We'll do our standard lift. We want to make sure it comes up even. At that point, we're ready to travel. We will come out into the aisleway and then direct path to the service module.
International Space Station is the largest, most complex international scientific and engineering space project in history, and the world's largest endeavor into space to date. Boeing has been the International Space Station's prime contractor since 1993 and is responsible for the design, development, integration, testing, delivery, and sustainment of U.S.-built elements. Boeing supports a variety of capability enhancements that will enable use of the ISS through 2024 and beyond, including
Touchdown Starliner. We're touching down in the desert of New Mexico, marking the completion of Orbital Flight Test 2.
Ascent begins at T-0, liftoff, the end of the countdown, and the beginning of the mission. Shortly afterwards, at T+12 seconds, the rocket rolls, lining up Starliner with its target orbit and putting the astronauts in a heads-up position. Then, around T+40 seconds, max Q starts. That's also known as max aerodynamic pressure. This is a critical time when the atmospheric forces reach their highest. Next, at about +1 minute 35 seconds, the two solid rocket boosters run out of fuel and burn out, and about a minute later they separate from the booster. The Atlas booster engine continues to burn for almost 2 more minutes. Then at approximately +4:30, booster engine cutoff, or BECO. About 5 seconds later, the booster separates, and so does the ascent cover on top of Starliner. At around 4 minutes 45 seconds, the Centaur upper stage ignites, continuing the push to orbital speeds. Then a little after 5 minutes, Starliner is free of the atmosphere and doesn't need additional aerodynamic support, and the aeroskirt is jettisoned. After a long 6+ minute push from Centaur, main engine cutoff, or MECO, happens around 12 minutes after liftoff. Then, when Centaur successfully separates almost 15 minutes after launch, ULA's job is done. But Starliner is not quite in orbit yet. After a 16-minute coast, Starliner ignites 4 of its orbital maneuvering and attitude control, or OMAC engines, for the orbital insertion burn, and then 31 minutes after liftoff, the ascent profile is complete.